Hi, welcome to another lecture on business mathematics. We were talking about speed, average rate of change, derivatives, and marginal rates. So this is going to be part 2 of this particular sequence. We said marginal rates are a standard concept in business mathematics. So you will see marginal cost, marginal revenue, marginal profit, and a whole host of other marginal variables. To explain them mathematically, we started talking about speed, that is familiar to us. We said when you compare distance traveled versus the duration or the time it took, the ratio of these two gives us a very useful concept, and it's a concept of speed. That falls in the category of average rate of change. We can have any two quantities that are related to each other, and as one of them changes, so will the other one. Then we calculate the difference in these two quantities as they change, and the ratio of them is called average rate of change. In ideal mathematical sense, this leads to the concept of derivatives, which we are going to talk about today. And they all are an umbrella that contains the concept of marginal rates. So let's go ahead, take a look at a few examples of calculating average rate of change. So last time we talked about the derivatives. So we are going to build through a sequence of examples to arrive at the same concept. So suppose I have a function, y is equal to, call it f of x, and let's have a simple function like 5x plus 6. I ask what is the average rate of change of f of x or y for x in interval from 2 to 7. Well, let's go ahead and investigate this thing in several different ways. What does this mean? Average rate of change. A function is given to us. Here's our function. And an interval is given. What's the average rate of change? So we said the average rate of change several notations for it. One of them is called delta y over delta x. Okay, so what is delta y? Another way to describe that is delta f over delta x, either one. So when I want to calculate this thing, it means I'm going to figure out what this function is at each of these two endpoints. That is, I'm going to calculate what is f at 7 and what is f at 2. And delta x simply means how much did x change by, so 7 minus 2. So delta y is a change in y, delta x is change in x. Now then we go ahead and calculate what is f of 7. F of 7 is, well, 5 times 7 plus 6. So we replace x by 7 and figure it out. 5 by 7, 35, and 6 is 41, of course. And f of 2, that is 5 times 2 plus 6, and that is, of course, 16. So how much did this thing change? F of 7 minus f of 2, that's going to be 41 minus 16. And what is that? So that is, of course, 25. That is our numerator, delta f or delta y. So what we have is delta y or delta f, either one is 25. How about delta x? Delta x is how much x changed. We went from 7 to 2, and this one changed by 5. The ratio of these two, delta y over delta x, it becomes 25 over 5. And that is, of course, just 5. Okay, if you do this exercise with any function like this, mx plus b over any interval, out comes m. So that thing, this whole process can be simplified by saying that if I have a line mx plus b and any 2 points, any 2 number values for x, the result of this whole thing is going to be m. Well, that's rather easy to understand why that is. So let's go ahead and do a quick graphing. I'm not going to graph to scale, just quickly indicate. So we have some linear function, y is equal to 5x plus 6. So it looks like this. Again, I'm not drawing to scale, just so that we are quick here. So at beginning, we are at the point 2. At the end, we are at, say, some point 7. At 2, we are at the height 16. And at 7, we were at 41. So from 2 to 7, this delta x from 2 to 7, that is just 5. Delta y from beginning to end, 41 minus 16, that is 25. So we call this one the run. Our run is 5. And we call this one rise. Rise is 25. Ratio of rise to run, well, what's that going to be? Rise to run. Well, that's 25 over 5. What is the rise to run for a line? The rise to run is always the slope. So it's not a surprise that we got that number 5 back at the end. Now let's go ahead and do another example where the answer is not as clear as this one. So suppose I have f of x, so we have another function. Again, we like this generic name f for every function, so it's fine. We are going to take f equal to x squared. And the interval over which I'm going to calculate the rate of change, average rate of change, let's say we go from 3 to 7. What is the average rate of change? Average rate of change. Well, always delta y to delta x, or if you wish, delta f or delta x. If you want to use the letter y for the output, or you want to use the name of the function, either one. Well, what do I need to do? Well, I need to figure out what is f at the end, f of 7. Well, that's 7 squared. What's f at the beginning? Well, f of 3 is 3 squared. And that is 49, and that is, of course, 9. So delta y or delta f is how much this changed. So 49 minus 9 is a nice 40. How about delta x? Delta x is changing x. So that's 7 minus 3. That is 4. So what is delta y over delta x? Well, that's going to be 40 for delta y, 4 for delta x, and ratio is a nice 10. Okay, we found the average rate of change. Average rate of change is 10. What does that mean? In picture, what does that mean? Well, y equal to x squared is a famous parabola. We talked about parabola before, lots of uses for parabola. So it looks something like this. Again, I'm drawing this thing quickly, not paying attention to too much detail or getting my scales perfect, but it looks something like this. So the beginning of our interval is 3, somewhere it's 3. So that is where y is x cubed, so that's going to be 9. Again, don't get distracted by the fact that my 9 and 3 almost same length here. That's in the y-axis, that's in the x-axis. So I'm not drawing to the regular scales, just to be quick. End of the interval is 7. So suppose 7 is here. And then, of course, on the y-axis, we are going to get to 49. So, how much did we rise by? We went from 9, we went to 49, so that is 40. How much did we run by? Run 7 minus 3, that is 4. Well, what we are after is a ratio of rise to run. What is rise to run? Rise to run will be slope. So the beginning point on the curve and ending point on the curve get connected by a line. That line has a name, it's called secant line. For whatever reason, it's called secant line. The slope of that line is the ratio of rise to run, and its slope is 10. What that number is what we are referring to as average rate of change for this particular function. So we had x squared, we had a particular interval in mind, and then we calculated it and we got 10 for it. Now, unlike the case of a line, for the line we said no matter which 2 points you use, you always end up with the same answer because you're just getting slope of the line. That's not the case for any other function. So linear functions are nice in that their slope is the same all over the place. But any other function is going to behave differently. So if I take this function again, so suppose I pick y equal to f of x, same function, x squared. I change my interval to 1 to 2. What is the average rate of f over interval from 1 to 2? So it's delta f over delta x. Delta f means calculate the f at the beginning and end and subtract. Delta x simply means take beginning and end and subtract. This has to be in the same order. If 2 is at the beginning and then a 1 at the end, or if you want to calculate, put a 1 at the beginning and a 2 at the end, but do the same thing in numerator and denominator. So f of 2 means 2 squared. F of 1 means 1 squared, so it's 1 squared over 2 minus 1. So of course that is 4 minus 1 over 1, and the ratio becomes 3. So here we got average rate of change to be 3. Over there we got it to be 10. So generally, if you pick a new pair of beginning and end, you get a different rate of change. Okay, so we tried this function x squared with the interval 1, 2, I got 3. With the interval 3, 7, I got 10. We can do this thing in more examples, but we think, can I make it a shortcut that can I make a formula with a general interval going from say A to B and get the answer? That would be killing lots of birds with one stone, if you wish. We are so let's go pose this question differently. So for the third time, we are going to aim a bit higher. So okay, I have the same function, y is equal to f of x is equal to x squared. The interval, instead of giving particular numbers, I say a and b. So if a and b are 1 and 2, I should get that. If a and b and 3 and 7, I should get the previous result. So what do? We say delta f delta x. Calculate f at the end point. So I take an end point, put it here, and I get b squared. Take the starting point and put it in the formula. I get a squared. I'm supposed to calculate the difference of f at the beginning and the end. Delta x simply refers to the length of this interval from a to b. How much did we change? Well, that is b minus a. So that's our ready-made formula. Now comes the idea, can I simplify this? Can I make it even simpler than it was? Well, we remember an idea from our algebra class. If I have b squared minus a squared, I can write it as b minus a times b plus a. Is that right? Do you remember that? Why is that so? Because I can verify by multiplying. B times b is b squared. B times a, well, that's ba. A times this a times b minus ab. Minus a times a, that's minus a squared. The magic is that these two middle terms cancel out, and I do get that b squared minus a squared. So that's called an identity, an important factorization formula. You have used it in when you are solving the quadratic equation and such. Now we state it. Let's put it in a box because it's a very useful formula. So the numerator, I can write it as b minus a times b plus a. The denominator was just b minus a. And of course, let's put this in parentheses. This is same as that. They cancel out. Of course, a and b have to be different, otherwise we'll have an issue of dividing by 0. Aside from that minor point, these two cancel out, and I get this result, b plus a. Okay, that's as simple as we can make it. So if a and b are 1 and 2, then b plus a would be 1 plus 2, and that is 3. So how can I make a shortcut from that to the here? Just add these two numbers. Is it still true here? So for 3 and 7, we got 10. Well, of course, 3 plus 7 is 10. So that's a discovery that we have here. The average rate of, average rate of change of y is equal to x squared over interval a b is a plus b. Now we go for next level up. Instead of average rate of change, we have something called instantaneous rate of change. Instantaneous means, what if A and B are very close to each other? Let me explain it like that. If you are traveling on a highway and you go from, say, Beaumont to Houston, and it takes you 2 hours, and there's heavy traffic and this and that, and as soon as you get out of traffic, you start going very fast in 80 miles an hour, 90 miles an hour, and so on, and the police stops you, you cannot complain about the traffic that you were sitting in. The police measures your speed at a particular moment. It doesn't matter to him that from Beaumont to Houston it took you 2 hours to go for 85 miles. What he cares about is that at the moment that he had his laser gun on your car, for that very short duration of time, how fast were you going? So average rate of change is like that concept of going from Beaumont to Houston, 85 miles, how much it takes, that's fine, that's your average speed. But at a particular moment on the highway, how fast were you going at that very moment? That would be the instantaneous rate of change. So if I have some number C, and I choose some number close to it, A before it, and some number close to it, B after it, then average rate of change from A to B would be A plus B. If A and B are both of them close to C, then A plus B will be close to 2C. If A is close to C, B is close to C, A plus B will be C. So we can say the instantaneous rate of change of y is equal to x squared at C is 2C. So if A and B, both of them are close to C, then A plus B is close to 2C, and that is what we call the derivative. So another way of packing the same information, instead of bringing in one more letter, we just stick with our original x. I say if I have x and A is a little bit before it and B is a little bit after that, then A plus B will be close to 2x. So we can say derivative of y equal to x squared at x is 2x. We show this thing, we said y prime is equal to 2x, or we write it dy dx is equal to 2x. You remember last time we said that this is a Newton notation, this is a Leibniz notation. At either case we have the 2x coming up. So what was the meaning of a derivative or average rate of change? So again, let's go back to our trusty parabola. So we have a picture looking like this, so there's the other half too. So suppose you have this point C, and you put A very close to it on the left, B very close to it on the right, and then you ask what is the slope of this line. Well, when these 2 points are very close to each other, that so-called secant line turns into the so-called tangent line. So you have this tangent line. What is the slope of that tangent line? Slope of tangent line to y equal to x squared at C is whatever this quantity is 2C. So for example, slope of tangent line to y equal to x squared at 5 will be 10, because twice 5 is 10, and so on. Okay, now let's go ahead and do this exercise all over again for some function slightly more sophisticated than this one. So I go ahead And now upgrade to y is equal to x cubed. I want to find out the average rate of change and instantaneous rate of change of this thing at a certain point. What we need is a little bit higher up version of this formula. So let me go ahead and open this topic. So I am going to put this thing on the side for a moment. We said b squared minus a squared. We practiced this thing a moment ago. Is b minus a times b plus a. You can imagine if I am dealing with cube, then the numerator will be b cubed minus a cubed. Can I figure out how does that one factor? You might have seen this thing in your algebra class. If not, let's go practice it. This one turns out to be this factor is always the same, b minus a. The other factor starts becoming bigger and bigger. This becomes b squared ba plus a squared. The second factor, the big one, so we have like a short one and a long tall one, the second one starts to form up. Let's go ahead and check to see, well, why is this thing equal to that? I take b and multiply it by each of these three items. So I'll have b cubed plus b squared a plus ba squared. So okay, I took b multiplied by all three of them. Next, I go take a and multiply that by each of these three items. So I will have minus ab squared, a times b times a is minus a squared b, and a times a will be a cubed. Look at the magic, that these two cancel each other out. These two cancel each other out, and out comes b cubed minus a cubed. There's a particular pattern to this thing. You see that b squared, then power 1, then power 0 a, power 0, power 1, power 2. So that's a very nice pattern to it. So what does this mean? Suppose I want to find average rate of change of y is equal to f of x is equal to x cubed over interval from a to b. So what is my delta y over delta x, or delta f over delta x? So we calculate f at the end point, b cubed. At the starting point is a cubed. X itself changed from a to b. Now numerator is an example of this identity. It factors as b minus a times b squared plus ba plus a squared. Denominator is always b minus a, and this one always cancels with that one. That cancellation is a crucial part of all these calculations. You have to always cancel to see the light at the end of a tunnel. What do we get is b squared plus ba plus a squared. So we have the following: average rate of change of y is equal to x cubed over the interval from a to b is b squared plus ba plus a squared. Now we are going to play the same game as we played last time. I will say if a and b come close to each other, okay, that's the story of policeman on the highway catching you. He doesn't care about half an hour ago you were in the traffic and what happened there, and your time from Beaumont to Houston took 2 hours or something. He cares about well, when he's putting his laser gun on the car, from beginning to end of that process is extremely short period of time, microsecond or some whatever that is. So it's not that we are going an hour earlier, an hour later to see uh, how much did your distance change over 2 hours. Rather, he's interested in knowing what's the distance change over 2 milliseconds or something, not 2 hours. So A and B will be close to each other. When that is the case, instead of average rate, we call it instantaneous rate. Instantaneous rate of change of y equal to x cubed. Then instead of saying over, we are interested at some particular moment. It's like the policeman, at the moment I put my laser gun, what happens at that. So A and B, both of them are two numbers extremely close to C. Tad bit to the left, tad bit to the right, but C is stuck somewhere in between those two. So these three are all c squared, another c squared, and another c squared. So B is very close to C. So B squared is very close to C. B and A are very close to C. So B times A becomes just C squared. And A is very close to C. So that's also another C squared. So we have three of them, and then you put it together is 3C squared. Now compare this thing to what we had before, see if we can see a trend. Where did I write this? The average rate of change of x squared at C is 2C. For x cubed is 3C squared. Let me write both of them in the same panel so that you can compare. Instantaneous rate of change of y is equal to x squared at C is 2C. Now, can you guess for me what will happen if I have y is equal to x to power of 4? Do you see a pattern here? This is power 2. Perhaps you want to pause this thing for a second and find for yourself. What do you think the answer is going to be here if I start with x4? So you see, did you guess? 3 is this 3 that shows up here, and that is one notch lower than the exponent that you had. 2 is the coefficient here, and this is really C1. 1 is one notch less than this. So in this case, this is going to be 4, and C to what power? Yes, if you said 3, then you are correct. In the same style, if I had x to power of 5, then this is going to be 5c to power of 4. If I had y to power x to power of 6, this is going to be 6c to power of 5, and so on. So that is how we get the derivative of a function. So we write it like this now. dx to power of n over dx. Another notation for it is x n and a prime on top of that. This is capturing whatever we are doing here, and the result, instead of focusing at some arbitrary point C, instead of dragging one more variable into our problem, we just report it at the point x itself. So if I'm doing at x, this is going to be 2x, this is going to be 4x cubed, it's going to be 5x to the power of 4, and so on. This is going to be n x to power of n minus 1. What is this? This is called derivative of a power. Derivative of x to power of n is n to power of x minus 1. And then what if I have several different powers? Suppose I had x to power of 3 plus x to power of 5. I want to differentiate the sum of these two. The rule is that you take each of them and differentiate separately and add them together. That works for addition or subtraction only, not for anything else. So only the simplest things can be treated this way. Take a derivative of this one, so 3x squared, and this one is going to be 5x to power of 4. Well, what if I had x cubed plus x cubed? That looks rather odd, but let's go ahead and do it. This is 3x squared plus another 3x squared. Of course, you say, well, wouldn't it have been a lot better to write this in as 2x cubed? Of course, yes, that's better. And then how about here? This is twice times 3x squared. So in general, if I have a number times x cubed and then I want to differentiate, I let that number be and then I multiply it by 3x squared at the end. That rule applies in general if I have a number times x to some power n and I want to differentiate. That number stays on the side. Derivative of x to power of n, as usual, is n x to power of n minus 1, and then you write it without the parentheses, becomes a n x n minus 1. Let's go ahead and practice this thing in a problem. Suppose I have 5x cubed plus 11x to power of 7. I want to differentiate that. So 5 times 3, that's going to be 15x2. 7 times 11 is 77x6. So what's the short step? Power multiplied by the coefficient in front. So that's going to give me my new coefficient. Power lowered by 1 notch. That's my new exponent. 7 times 11 is 77. And 7 comes down to 6, and that is the final answer in this case. So let's repeat the rule that we had last time. If I have some number times x to power of n, and then some other number times x to some power m, and some other number x to some power p, and then I want to differentiate, each exponent multiplies the coefficient in front, a n x to power of n minus 1, b m x to power of m minus 1, cp x to power of p minus 1, and if I have more of them, then I'll have more of these. Now, if you go ahead and take a calculus class, then we tell you, other than this operation of addition and subtraction, if I had multiplication or if I had division and if I had some other operation, what would I do in all those cases? Well, there are more sophisticated rules that applies in those cases, but for the moment we are not going to be dealing with them. Okay, so that was our second lecture for covering the issue of speed, average rate of change, derivatives, and all of these formulas get to be applied and used in the context of calculating marginal rates. So marginal rate, suppose I want to calculate marginal cost. What do I mean by that? So we're going to have that in the next lecture, but let's just prepare for that. So what is marginal cost? So what is cost? Cost, typically shown by letter C. If you have a factory and you are producing some gadget, you decide on your output level how many gadgets do you want to produce, 10,000, 20,000, 30,000, or whatever that is. So cost of X will be number of items produced. Well, you might think, well, just take the cost of one item and multiply it by X, and then you'll get the whole cost. But that's not the case. A business has a startup cost. You have to spend a lot of capital to get something started, and then the materials that you buy, that depends at what volume you buy them. So things are not as straightforward as a straight line or something. So cost of producing X units is some complicated function by itself. Marginal cost is the average rate of change of this, meaning suppose you have production level X and then you go up to production level X plus 1. So at the beginning you have some cost. If you go up one more, well, your cost is going to be a little bit more. That's the change in cost. What is the change in production level? Production level at the second stage, X plus 1. At the first stage, it was just 1. So your production has gone up by one item. So this is just 1. So this is C of X plus 1 minus C of X. So marginal cost refers to the difference between this function at X and X plus 1. Now when your production level is high, if you're creating tens of thousands of some gadget, this can be approximated by C prime. The derivative that we learned, C prime, is approximately, that is, these two values are very close to each other. That is equal to Cx plus 1 minus Cx, approximately, depending on the situation. So that's the concept of marginal cost. In the same fashion, the marginal revenue and the marginal profit, they have a similar characteristic, that they are revenue from producing X item and selling it versus revenue producing one more item. The difference between those two will be approximately equal to the derivative of revenue function. So our prime of X is approximately R of X plus 1 revenue from selling one more item. That is your marginal revenue. And same fashion, marginal revenue. In the same fashion, you have a marginal profit. Marginal profit, P prime of X. That is profit, extra profit, if you actually have extra profit, to make from producing one more item. Okay? And so that's how the derivative gets into business calculus or business mathematics. The marginal rate that you're calculating is approximately same as the derivative. Okay, we are going to have more examples in the next lecture. Until that time, good luck and God bless.